Hey, good morning. Can you hear me? How are you? Can you hear me? Can you hear me? Can you? Can anybody hear me? I'm waiting for you, for your answer. Can you? Can you hear me? Can we start? Okay, thank you, thank you. Forget about my image, this is not important. And now, please, we want to start by correcting some exercises you had to do the other day. So please, you had to take before you your notes and in page number 10, you have there this exercise 19, and you have to label by the drawings if they are cases of reflection or refraction. Remember that we have specular reflection when we can see very clearly the object. Diffuse reflections is the opposite. Okay, we only can see some colors. And refractions when we can see through the object. And now you have here a magnifying glass, lupa, magnifying glass. What do you think this magnifying glass is an example of specular reflection, diffuse reflection, or refraction? What do you think? What do you think? Remember, reflection is when you can see through the object. Sorry. Refraction, you can see through the object. And reflection is when you can only see some colors of the object. What do you think? Magnifying glass. This is an example. Yes, Ines. This is an example of refraction because light hits this crystal and it refracts because it passes from air to another medium, in this case a crystal. And can you see any other object here that is another example of refraction along with a magnifying glass? Any other? Maybe the shine screen, or maybe a prism, or a key, or eyeglasses, rainbow. What do you think? Not specular, Miguel, not specular. A magnifying glass is an example of refraction because you can see through the object. And any other example can you find here between these 8 objects? Anyone? The glasses, okay, the eyeglasses. The same example of as a magnifying glass. Yes. What about the shine screen? You can't see through the screen, but maybe if it is very shiny, you can see yourself as in a mirror. This is another example. What do you think? A shine screen and a mirror are examples of refraction or reflection. What do you think? A shine screen and a mirror are examples of, what do you think? Remember, refraction you can see through water, for example, magnifying glass, eyeglasses. Reflection, you can only see colors and the shape of the objects. What do you think? Okay, could be a diffuse reflection in S, but if it is very shiny, really shiny, you can see it as in a mirror. You can see yourself as in a mirror. So a mirror and a shiny screen could be examples of reflection. Remember, specular. This word, specular, is a word that comes from Latin. Specular means mirror, espejo, specular. Okay, so a mirror, a shiny screen, and the top of the water in a pond are examples of specular reflection. And a rainbow is another example of waiting for you. Some of you tell it a moment before. A rainbow is the same example as a magnifying glass, as eyeglasses, as a prism, and this is an example of talking about a rainbow. A rainbow. Waiting for you. A rainbow. So, a rainbow is a phenomenon that occurs when light passes through water drops or water vapor. And no, this is not reflection. This is not reflection. So you can see the light decomposed in 7 different wavelengths, 7 different colors. Remember, this could be red and this could be violet. So this is reflection. Very good. What about the key? What is a key example of? What about the key? Can you see through the key? If not, this is not refraction. This has to do with reflection, but you need to choose between specular or diffuse. What do you think about the key? A key is an example of waiting for you. You are having an exam, kind of exam about that. You need to do your exercises. Yes, Ines, very good. A key is an example of diffuse reflection. Very good. Now, before continuing, I'd like you to watch kind of documentary about the basics of light. And pay attention now.
What if you could only see one color? Imagine, for instance, that you could only see things that were red, and that everything else was completely invisible to you. As it turns out, that's how you live your life all the time, because your eyes can only see a minuscule part of the full spectrum of light.
Okay, so the spectrum of light is composed of many colors.
Different kinds of light are all around you every day, but are invisible to the human eye. From the radio waves that carry your favorite songs, to the X-rays doctors use to see inside of you, to the microwaves that heat up your food. In order to understand how these can all be light, we'll need to know a thing or two about what light is. Light is electromagnetic radiation that acts like both a wave and a particle. Light waves are kind of like waves on the ocean. There are big waves and small waves, waves that crash on the shore.
So light waves are the same way as the waves in the ocean. So this is a comparison.
Or one right after the other, and waves that only roll in every so often.
There are many kind of waves, okay? This is a kind of wave, and the other, very little, are different.
The size of a wave is called its wavelength, and how often it comes by is called its frequency. Imagine being a boat in that ocean, bobbing up and down as the waves go by. If the waves that day have long wavelengths, they'll make you bob only so often.
So, imagine this is an example. So, here you can see a wave, but with a very low frequency, okay? And this is a very long wavelength, okay? So, this person is able to catch fish very normally.
Or at a low frequency. If the waves instead have short wavelengths, they'll be close together and you'll bob up and down much more often, at a high frequency.
Okay, so, very good.
Different kinds of light are all waves. They just have different wavelengths and...
Can you see? These are the wavelengths of the red. This is the orange and green. Can you see the difference? It's very similar to the waves in the ocean.
Frequencies. If you know the wavelength or frequency of a wave of light, you can also figure out its energy. Long wavelengths have low energies, while short wavelengths have high energies. It's easy to remember if you think about being in that boat. If you were out sailing on a day with short, choppy waves, you'd probably be pretty high energy yourself, running around to keep things from falling over. But on a long wavelength sea, you'd be rolling along, relaxed, low energy. The energy of light tells us how it will interact with matter, for example, the cells of our eyes. When we see, it's because the energy of light stimulates a receptor in our eye called the
Okay,
retina.
so this is interesting. Next year you're going to study the human eye. So this is a hole, and this is the pupil, and this is light energy that comes into our eye. Okay, and here this is refracted to this part. This is retina, the retina. Okay, the retina. This part here, can you see? This is the retina. The retina has nervous terminals, okay, nerve endings that can turn light energy into electrical and electrical energy that go for our brain.
Our retina are only sensitive to light with a very small range in energy, and so we call that range of light visible light. Inside our retina are special receptors called rods.
Okay, this is the retina. This is the two different kind of cells we have there. One of them are called rods, okay, and the other are called cones. Cones can detect the colors, and rods can only detect the brightness or darkness. This is interesting. This is for next year, and this is the retina. Okay, and that's the place when light is turned into electrical impulse.
Cones. The rods measure brightness, so we know how much light there is. The cones are in charge of what color of light we see, because different cones are sensitive to different energies of light. Some cones are more excited by light that is long wavelength and low energy, and other cones are more excited by short wavelength, high energy light. When light hits our eye, the relative amount of energy each cone measures signals our brain to perceive colors. The rainbow we perceive is actually visible light in order of its energy. And once
Okay, so this is the rainbow, okay, and this is an example of refraction. Okay, but these are the only colors we can see, okay, from red to violet. There are many other different waves that we can't see inside light.
side of
Microwaves.
the rainbow is low energy light we see as red, and at the other side is high energy light we see as blue. If light shines on us that has an energy our retina can't measure, we won't be able to see it. Light that is too short wavelength or high energy gets absorbed by the eye's surface before it can even get to the retina, and light that is too long wavelength doesn't have enough energy to stimulate our retina at all.
Can you see here? This is the refraction of light. Okay, this is air, and this is another different medium. Okay, this is refraction, and this is the change of direction of light.
The only thing that makes one kind of light different from another is its wavelength. Radio waves have long wavelengths, while X-rays have short wavelengths. And visible light, the kind
In
you
the
can
middle, so radio waves, we can see them. X-rays, we can see them. We only can see middle wavelengths light.
actually see is somewhere in between. Even though our eyes can't detect light outside of the visible range, we can build special detectors that are stimulated by these other wavelengths of light, kind of like digital eyes. With
So in this moment, this person is using a device that enables her to see invisible rays of light, but that we can't see with our naked eye. We need some binoculars, some tools like that.
these devices, we can measure the light that is there, even though we can't see it ourselves. So take a step back and think about all of this for a moment. Even though they seem different, the warmth you feel from a crackling fire is the same as the sun shining on you on a beautiful day. The same as ultraviolet light you put on sunscreen to protect yourself from. The same thing as your TV, your radio, and your microwave. Now those examples are all things here on Earth, things you experience in your everyday life. But here's something even more amazing. Our universe gives off the full spectrum of light too. When you think of the night sky, you probably think of being able to see the stars shining with your own eyes. But that's just visible light, which you now know is only a tiny part of the full spectrum. If we had to draw the universe and could only use visible light, it'd be like having only one crayon. Pretty sad. To see the universe in its full spectrum, we need to have the right eyes. And that means using special telescopes that can help us see beyond visible light. You've probably heard of the Hubble Space Telescope and seen its beautiful pictures taken in
Now,
visible...
attention, this is a kind of light in the universe we can't see. We need some special devices, so the Hubble telescope is one of them. So when we are seeing stars, the light of stars, this is just a tiny fraction of the light. Only with this telescope we can see the rest of the waves that comes into light. Okay, and this is the image. This is a galaxy. Okay, this is a galaxy. We can't see it with the naked eye. We need a special telescope. The Hubble telescope is one of them.
and ultraviolet light.
This is another galaxy. Okay, it's composed of billions and billions of stars.
You might not know that there are almost 20 space telescopes in orbit. Missions that can each
Galaxies, different galaxies. We can only see with special devices.
see part of the full spectrum of light. With telescopes acting as our virtual eye,
This is our galaxy. Okay, this is the Milky Way. The Milky Way. Okay, la Vía Láctea. Milky Way. This is our galaxy, and we are more or less in this position, more or less, the solar system.
eyes, both in space and here on Earth, we can see some amazing things. And the coolest thing of all, no matter the wavelength or energy, the light that we see out in the distant universe is the same thing as the light that we can experience and study here on Earth. So since we know the physics of how X-ray, ultraviolet light, or microwaves work here, we can study the light of a distant star or galaxy and know what kinds of things are happening there too. So as you go about your daily life, think beyond what your eyes can and can't see. Knowing just a little bit about the natural world can help you perceive the full spectrum around you all the time.
So very good, very interesting documentary. Very good. So let's go now to the next exercise. So exercise number 20, and you have to choose the only right answer here. So I'd like you to take part in this correction. So 21, you are shopping. When looking at the fruit, you can see an orange. Why is the orange orange? You can choose between A, all colors but orange are reflected of the orange. All colors are reflected. Could be B, all colors are absorbed by the orange, all of them. C, all colors are absorbed by the orange except orange. And D is a combination of red and white light. What do you think is the correct answer? Okay, for 21, A, B, C, or D? What do you think? What do you think? So, we need to choose between all colors but orange are reflected of orange. If they are reflected, we can see all of them, but we can only see orange. So A is very difficult. B, all colors are absorbed by the orange. If all of them are absorbed, we can see none. So we only could see black. So impossible. C, all colors are absorbed by the orange except orange that is reflected. And yes, that's the reason this is the correct answer. Okay, we see an orange because all the rest of colors are absorbed by the orange, and orange is reflected. Good. 22. What happens when light passes through a cup of water? What passes? And we can choose between A, the light is reflected. the light is refracted. Remember, reflected is when you cannot see through it. Light is refracted is that you can't see through it. A light passes straight through, so not bent, and light rebounds, as in a mirror. What do you think is the correct answer? 22. Waiting for your answer. 22. Yes. B. So light is refracted. Very good, Ines. Very good, Julia. Very good, Valeria. Very good. Now, go for the next question. So, when light passes through a prism, what do you see? White light, black light. Black light, by the way, doesn't exist. The colors of the spectrum. Remember the spectrums? The spectrum is the set of the different colors we can see. A sickly gray. What do you think? A, B, C, or D? What do you think? So 23. When light passes through a prism, what do you see? White light, black light doesn't exist. The colors of the spectrum, see? A sickly gray. What do you think? Yes, you're right. So we can see the colors of the spectrum, and these colors are called rainbow. Very good. So next, 24. Which of the following object doesn't refract light? Mirror, glasses, microscope, a magnifying lens. Okay, mirror, glasses, microscope, magnifying lens. What do you think? A, B, C, or D? What do you think? A mirror. Remember, refraction is when you can see through the object. Glasses, you can see through the object. A microscope, you can see through it. A magnifying lens, you can see through it. So the only different answer is A. Yes, you're right. So mirror. Mirror is the correct answer in this case. Okay, let's finish this part. Light that passes through the lenses in a pair of binoculars is light that passes through. So reflected, refracted, absorbed, bounced off. What do you think? 25. What do you think? A, B, C, or D? What do you think? It's not absorbed. In a pair of binoculars, you can see through them. So if you can see through them, this is not reflected, this is not absorbed, this is not bounced off. It must be refracted. Okay, this is the correct answer. Very good. Now please go for your text section, and you can see that light energy can be transformed into some other forms of energy, and we have some examples here in our text. So from light energy to chemical energy, and the best example is the sun. Why? Because the sun is the best example of light energy. So the sun gives plants light energy, which is converted into chemical energy during. So this is a transformation from light energy to chemical energy. This is another example. You know all about that. And this light energy powers most things in nature, because plants use light energy to grow, and then most animals get their energy from eating plants. So that's why light energy from the sun is all important to life on Earth. Without light energy from the sun, there couldn't be any life on Earth. So this is an example of transformation from light energy to chemical energy. Another example we have from light energy to thermal energy. And you have here this text. Light energy can also be converted into thermal energy when, for example, a light bulb works. When you see a light bulb working, and you touch this light bulb, you are burned. Okay, why? Because light energy can be converted into thermal energy, heat energy. Okay, the sun is another example. The sun heats up your black shirt or a brick wall outside. And another very interesting example of transformation is light energy change into electricity. And we have the example of the solar panels. Okay, all of you know that solar panels are able to change light energy into electricity. And this electricity that is produced by solar panels can be used afterwards. It's eco-friendly and cost-effective too. Very good, very good. And I have for you another interesting documentary about light producing electric energy. Pay attention.
Light produces electric energy. In the following experiment, we are going to show that light is in fact energy and can be...
So this part here, this is a kind of solar panel, very little solar panel. The same as you can see in many calculators. Okay, here in this part. Pay attention. So here, this is a device that detects if there is any electrical circuits going on. Okay.
Be converted to different energy forms, such as chemical energy, electric energy, etc. We will show how light coming from a lamp produces electricity by using a device called a photovoltaic panel. We will need a lamp, a photovoltaic panel.
A photovoltaic panel is the same kind you can find in any calculator. Okay, and this is powered by the lamp that we saw before.
An LED, light-emitting diode. A voltmeter.
This voltmeter is able to detect if there is any electric current going on.
Connection wires. Black cardboard. We cover the panel with a piece of black cardboard so that it is not exposed to the light at all.
Okay, so we have here the cardboard. Okay, this is the black cardboard, and the light coming from the lamp doesn't reach these panels that are behind.
We connect the voltmeter pins to the connection poles of the panel. We observe that the voltage is almost zero.
So, no electricity. Okay, scarce electricity here.
We remove the cardboard and shine the lamp on the panel. We measure the voltage between the panel poles. The voltage has increased significantly. By shedding light on the cells of the photovoltaic panel, the proper amount of energy is given to the electrons of a certain area, so they can move directly to another area. Therefore, two areas with opposite charge are created. Consequently, voltage appears between those areas. We cover the panel again. We connect the poles to the LED pins. This is a simple electric circuit. By removing the cardboard, we expose the panel to the light. The LED lights up. The panel now works like a battery, providing electric energy.
Very good, very good. Interesting. And now, please, I'd like you to watch. We have time to watch another interesting documentary about how solar panels work. Pay attention to it.
Así que quieres aprender inglés. Aquí tienes 3 mitos que son
It's
completamente
an
falsos.
advertisement,
Uno, debes
so
hablar.
good.
The Earth intercepts a lot of solar power, 173,000 terawatts. That's 10,000 times more power than the planet's population uses. So is it possible that one day the world could be completely reliant on solar energy? To answer that question, we first need to examine how solar panels convert solar energy to electrical energy. Solar panels are made up of smaller units called solar cells.
And they appear to be black, not blue, black. And why is it? Because all colors of light are absorbed and they don't reflect any other colors. That's why they are black. You have an exercise in your notes about that.
Most common solar cells are made from silicon, a semiconductor that is the second most abundant element on Earth. In a solar cell, crystalline silicon is sandwiched between conductive layers. Each silicon atom is connected to its neighbors by 4 strong bonds, which keep the electrons in place, so no current can flow. Here's the key. A silicon solar cell uses 2 different layers of silicon. An N-type silicon has extra electrons, and
Have you ever heard of Silicon Valley in California? There, in this place, they are used to do experiments about silicon and about solar panels.
P-type silicon has extra spaces for electrons, called holes. Where the 2 types of silicon meet, electrons can wander across the p-n junction, leaving a positive charge on one side and creating negative charge on the other.
And this is electricity. This is electricity.
You can think of light as the flow of tiny particles called photons.
You know about that, photons. You remember these are photons, tiny particles, okay? And this is the straight line, but inside you have a lot of waves inside, okay? So straight line, and these are photons, but they are inside. They are traveling in waves, okay? But in a straight line.
Shooting out from the sun. When one of these photons strikes the silicon cell with enough energy, it can knock an electron from its bond, leaving a hole. The negatively charged electron and location of the positively charged hole are now free to move around. But because of the electric field at the p-n junction, they'll only go one way. The electron is drawn to the n side, while the hole is drawn to the p side. The mobile electrons are collected by thin metal fingers at the top of the cell.
Okay, and you are creating electricity. So light is transformed into electricity. One form of energy, light energy, is changed into another form of energy, electrical energy.
There, they flow through an external circuit, doing electrical work like powering a light bulb, before returning through the conductive aluminum sheet on the back. Each silicon cell only puts out half a volt, but you can string them together in modules to get more power. 12 photovoltaic cells are enough to charge a cell phone, while it takes many modules to power an entire house. Electrons are the only moving parts in a solar cell, and they all go back where they came from. There's nothing to get worn out or used up, so solar cells can last for decades. So what's stopping us from being completely reliant on solar power? There are political factors at play, not to mention businesses that lobby to maintain the status quo. But
These are reasons why we don't have a complete solar panels on Earth, okay? Although solar energy is a clean energy, eco-friendly energy. There are many interests.
for now, let's focus on the physical and logistical challenges. And the most obvious of those is that solar energy is unevenly distributed across the planet.
So, in Spain we have a lot of solar energy, but you go to the North Pole or the South Pole, there is less solar energy there.
Some areas are sunnier than others. It's also inconsistent. Less solar energy is available on cloudy days or at night. So a total reliance would require efficient ways to get electricity from sunny spots to cloudy ones, and effective storage of energy. The efficiency of the cell itself is a challenge too. If sunlight is reflected instead of absorbed, or if dislodged electrons fall back into a hole before going through the circuit, that photon's energy is lost. The most efficient solar cell yet still only converts 46% of the available sunlight to electricity.
This is one of the problems. Not all light energy can be turned into electricity. Okay, not even half of it.
And most commercial systems are currently 15 to 20% efficient. In spite of these limitations, it actually would be possible to power the entire world with today's solar technology. We'd need the funding to build the infrastructure and a good deal of space. Estimates range from tens to hundreds of thousands of square miles.
This is a lot. This is a lot of surface.
Which seems like a lot, but the Sahara Desert alone is over 3 million square miles in area. Meanwhile, solar cells are getting better, cheaper, and are competing with electricity from the grid. And innovations like floating solar farms may change the landscape entirely. Thought experiments aside, there's the fact that over 1 billion people don't have access to a reliable electric grid, especially in developing countries, many of which are sunny. So in places like that, solar energy is already much cheaper and safer than available alternatives like kerosene. For, say, Finland or Seattle, though, effective solar energy may still be a little way off.
So very good, very good. And now, before ending this class, remember that very soon you got to send me your vocabulary part. Okay, check you have the whole of it complete. Okay, and you have to send me in very soon these two parts. What you have learned in this unit and what would you like to learn more about it. Okay, this is important. Very good, very good. Now please, we are going to finish this class, and we can see ourselves in just a few time.